is Karthik and I am from ITS section and my roll number is 2095191230. Today on Tech Talk, my topic is about phase change technology and the future of main memory. Let us see what is phase change technology and future of the main memory in further slides briefly. Phase change memory may enable continued scaling of main memories, but PCM has higher access latencies, incurs higher power costs, and wears out more quickly than DRAM. This article discusses how to mitigate these limitations through buffer sizing, rowing, caching, write reduction, and wear leaving to make PCM a viable DRAM alternative for scalable main memories. Over the past few decades, memory technology scaling has provided many benefits, including increased density and capacity and reduced cost. Scaling has provided these benefits for conventional technologies such as DRAM and flash memory. But now, scaling is a jeopardy for continued scaling systems might need to transition for conventional charge memory to emerge resistive memory. Charge memories require discrete amount of charge to induce a voltage, which is detected during the reads. In the non-volatile space, the flash memories must precisely control the discrete charge placed on a floating gate. In volatile main memory, DRAM must not only place charge in a storage capacitor but also mediate sub-threshold charge leakage through the access device. Capacitors must be sufficiently large to store charge for reliable sensing, and transistor must be sufficiently large to exert effective control over the channel. Given these challenges, scaling DRAM beyond 40 nanometers will be increasingly difficult. In constant resistive memories, use electrical current to induce a change in atomic structure, which impacts the resistance detected during reads. Resistive memories are amenable to scaling because they don't require precise charge placement and control. Programming mechanisms such as current injection, scale with cell size, phase change memory (PCM), spin torque transfer, magnetoresistive RAM (MRAM), and ferroelectric RAM (FRAM) are examples of resistive memories. Of this, PCM is closest to realization and imminent deployment as a NOR flash competitor. In fact, various researchers and manufacturers have prototyped PCM arrays in the past decade. 2PCM provides a non-volatile storage mechanism that is amenable to process scaling during writes. An access transistor injects current into the storage material and thermally induces phase change, which is detected during reads. PCM really relying on analog current and thermal effects that doesn't require control over discrete electrons. As technology scale and heating contact areas shrink, programs current scales linearly. Researchers project this PCM scaling mechanism will be more robust than that of a DRAM beyond 40 nanometer, and it is already been demonstrated in a 32 nanometer device prototype. 3. As a scalable DRAM alternative, PCM could provide a clear roadmap for increasing main memory density and capacity. Providing a path for main memory scaling, however, will, and here this is the diagram, metal chalcogenide heater metal axis, and coming to another diagram, here it is the storage and it is the word line and access device and a bit line. So let us see some more slides. PCM access latencies, although only tens of nanoseconds, are still several times slower than those of a DRAM. At present, technology notes PCM writes require energy-intensive current injection. Moreover, the resulting thermal stress within the storage element degrades current injection contacts and limits endurance to hundreds of millions of writes per cell for present process technologies. Because of these significant limitations, PCM is presently positioned mainly as a flash replacement. As DRAM alternative, therefore, PCM must be architected for flexibility in main memory for general purpose systems. Today's prototype designs do not mitigate PCM's latencies, energy costs, and finite endurance. This article describes a large range of PCM design alternatives aimed to make PCM systems competitive with DRAM systems. This alternative focus on four areas. They are row buffer design, row caching, wear reduction, and wear labeling. Coming to technologies and challenges. The PCM storage element consists of two electrodes separated by a resistive heater and a chalcogenide. The phase change material GST is the most commonly used chalcogenide, but others offer higher resistivity and improve the device electrical characteristics. Nitrogen doping increases resistivity and lowers programming current, whereas GS offers lower latency phase changes. GS contains the first two elements of GST, germanium and antimony, and does not include tellurium. Phase changes are induced by injecting current into the resistor junction. The heating the chalcogenide. The current and voltage characteristics of the chalcogenide are identically regardless of its initial phase, thereby lowering programming complexity and latency. The amplitude, width of the injected current pulse determine the programmed state. PCM cells are one transistor, one resistor devices comprising a resistive storage element and an axis transistor. One of the three devices typically control axis, a field effect transistor, a bipolar junction transistor, or a diode. In the further FET, scaling and large voltage drops across the cell will adversely affect gate oxide reliability for unselected word lines. BJTs are faster and can scale more robustly without this vulnerability. Diodes occupy smaller areas and potentially enable greater cell densities, but require higher operating voltages. This is about the PCM cells, and the PCM cells are having one transistor and one resistor devices comprising a resistive storage element and an access transmitter. We have seen this figure in before slides, and one of the three devices typically controls access. This is about the PCM cells. Let us see more in the further slides. The access transistors injects current into the storage material and thermally induces phase change, which is detected during reads. The chalcogenide's resistivity captures logical data values and a high short current pulse, which is also called as reset, increases resistivity by abruptly discontinuing current, quickly quenching heat generation and freezing the chalcogenide into an amorphous state. A moderate long current pulse reduces resistivity by ramping down current, gradually cooling the chalcogenide and inducing the crystal growth. Set latency, which requires longer current pulses, determines write performance. Reset energy, which requires a higher current pulses, determines write power. This is about the transistor injects, transistor injects, and this is about our topic. Cells that store multiple resistance levels could be implemented by leveraging intermediate states in which the chalcogenide is partially crystalline and partially amorphous. Smaller current slopes produces lower resistance and large slopes. This is the technology survey. Here there are some parameters, and according to the parameters there are some values given. This is about our topic. Thank you.